In this video, I want to look at two important lemmas about subgroups. In the examples of subgroups that we've looked at, the group identity element happens to belong to the subgroup, and if a particular element H belongs to the subgroup, it turns out that H inverse also belongs to the subgroup. Well, we want to prove that those are always true, and that's what these two lemmas are going to say. So our first lemma says this: if I let H be a subgroup of some group G, then the group identity inside G has to belong to H. And here's how the proof is going to work. We know that H itself is a group under the same binary operation that G uses. So there is a group identity for H. So there is I'm going to call it an EH inside H, such that H times EH is equal to H for all H's inside set H. But I also know that H is a subset of G. So I also know that H times EG is equal to H for all H's inside H. And this is going to let me figure out that EG and EH are actually the same thing. So let me put that as a goal. My goal is going to be to show that EH and EG are the same thing, and that will put EG inside H, since EH already has to belong to H up here. Well, let's actually see how I'm going to go about doing that. So here's what we're going to do. We're going to let little h be anything inside H. So we know that, let's see, I want to do this with my right identities. We know that H times EH is equal to H, and we know that H times EG is equal to H. This is because H is inside H, and this is because H is inside of G, since capital H is a subset of G. Now, these two H's, of course, are the same, so we can conclude that H times EH is equal to H times EG. And I do know that there exists an H inverse inside G such that H inverse times H is equal to EG, and I know this since little h belongs to G. So I'm going to pre-multiply this equation by H inverse. So we now have H inverse HEH is equal to H inverse HEG. And we can stick the parentheses in those places. And when we do, we get EG times EH is equal to EG times EG. Well, this particular thing, I know that that's just going to be an EG, but I have to think about this. What I know about EH is that it is the group identity element of H, so it has to live inside H, and H is a subset of G. So I know that EH does indeed live inside G, and this fact says that EG times EH has to be EH. So this justifies that particular inequality. And what I now have, when I look at it, is EH does indeed equal EG, and I know that EH is inside capital H, so that forces EG to be inside capital H. So I kind of want to state again what our lemma says, because I want to talk about its importance for just a minute as well. Lemma 1 says, if H is a subgroup of G, then the identity element inside the group G has to belong to the subset H. the contrapositive of a true lemma is also true, and the contrapositive of this particular lemma is an important statement in its own right. It says, if the group identity does not live inside some subset, and let me clean up my handwriting there. If the group identity does not live inside subset H, then H cannot be a subgroup of G. And this contrapositive gives us an easy way of testing whether or not some subsets are subgroups. If the group identity is not in the subset, then the subset's not a subgroup. Well, on to lemma 2. Lemma 2 says the following. Let's let H be a subgroup of a group G. So G is a group. And I want to let little h be any element inside capital H, and I'm going to let this awkward notation H inverse in G denote the inverse of H inside the group G. Then the inverse inside group G must belong to the subset H. The proof of this is going to be very similar to the proof of the previous lemma. What I'm going to do is I'm going to let H inverse subcapital H be the inverse of H inside the subgroup capital H. Now remember that capital H is a subset of capital G as well as being a subgroup. So I do know that H is inside capital G, and I also know that H inverse subcapital H is inside capital G because this has got to be inside capital H. My goal is to show that the inverse inside capital G is equal to the inverse inside capital H, and this guy, of course, is known to be inside set H, and that will force what I want up here in my conclusion of my theorem. So that's what I'm trying to want, and this will show that. So again, what I want to do is I want to think about how am I going to do this. So let's go to the next page and think about what we know. What do I know? Well, one thing I know is I know that EG is inside H as well as being inside G, and EG is the group identity in both groups. Let's just write it as in both groups. And so what I know is that if I look at, let's say, H times H inverse inside G, I know that that's going to be in G because H is an element of H, which is a subset of G, so H is indeed inside G, and this is the multiplicative inverse of H inside G. But I also know that H times H inverse sub H is equal to EG because H is inside of capital H, and EG is the multiplicative inverse of capital H, and that's the definition of H inverse inside the subgroup G. Now, since EG is the same thing, I can set these two things equal to each other. In other words, what I now know is that H times H inverse time sub G is equal to H times H inverse sub H. And what I'm now going to do is I want to pre-multiply by H inverse sub G. So we're going to pre-multiply by H inverse sub G. And let me make my notation very clear. So I'm going to look at H inverse sub G times H inverse sub G. And that's going to be H inverse sub G times H inverse sub H. And again, we're in a group, so I can put these parentheses around things. And this guy is known to be EG. So we get, let me make my notation just a little bit clearer. So we get EG times HG inverse is equal to, well, this is EG again, times H inverse inside group H. But now remember, this element lives inside H, which is a subset of G, so this element is inside G, and that means this side is just H inverse inside set H. Whereas this side, I know that this guy here is inside G, so this side winds up becoming HG inverse. So HG inverse and HH inverse are exactly the same thing. And what that means, of course, is that HG inverse, so the inverse of H inside group G, is equal to the inverse of H inside group H, which is of course known to be inside H, and so that says that the inverse of H inside group G does indeed belong to H. Now again, what I want to do is I want to state this lemma very clearly again and look at its contrapositive. So what lemma 2 is actually saying is, if capital H is a subgroup of G and little h belongs to capital H, then to clean the notation up, the inverse of H has to belong to the set capital H. The contrapositive of this statement is again true, because contrapositives of true implications are always true, and the contrapositive gives us an easy test for when something is not a subgroup. The contrapositive says if H is a subset of G and little h belongs to H and H inverse does not belong to capital H, then capital H cannot be a subgroup of G. In other words, if I have a set that has an element in the set and the inverse of that element is not in the set, I know that the set is not a subgroup.